So hi, everyone. Thanks for joining this talk. Today, I'm going to be talking to you about dataset versioning and how to do it the right way. I'm Tal, a product manager at lakeFS, previously an engineer and engineering manager who moved to the dark side of product management, which I love, by the way. I spend most of my free time baking and trying to get my one-year-old interested in it, and so far this has been a huge success. He developed an obsession to my mixer, as you can see. And the other cute thing that is here to say hi is Lottie, the axolotl, the lakeFS mascot, who is here to say hi. Our story begins more than 2 decades ago, when data warehouses outgrew the capacity of single machines and scaling them started to become costly or inefficient. So what did we do? We had to rethink the architecture. So we started to use distributed systems and to store multiple files on multiple disks. So if we wanted to store more data, we just bought more commodity hardware. But when we tried to query the data, well, that didn't scale so well. So fast forward 20 years, we got used to the concept of data lakes that are structured somewhat like this diagram. So at the bottom layer, we have the storage layer that has turned from self-hosted commodity hardware into object storage. Right on top of it, we have the open table formats that brought performance SQL to the world of big data. The third layer would be the metastores or catalogs that store those structured formats. If it is the legacy Hive metastore or newer catalogs such as Unity catalog, Glue, or Snowflake. And right at the top, we have the distributed compute engines that you're all familiar with that allow us to query such a huge amount of data. So how did we get from files on disk to petabyte scale data lakes? Well, this has been an evolution process. So in the early 2000s, Google published the famous MapReduce paper, who definitely revolutionized big data processing, bringing distributed computing into awareness. But the outputs of those MapReduce jobs turned out to be inefficient for large-scale analytics. So we had to shift to a more structured formats. So first, we tried to use CSV and TSV, who existed a long time before. But they also proved to be inefficient for more complex queries or aggregations, which led to the emergence of columnar file formats, such as Parquets or ORC or Avro, who were designed to solve these scale problems. But even with those columnar file formats, it was still very difficult to select specific data due to the lack of indexing in big data systems. And then partitioning was introduced, splitting files into directories according to logical segments. And the problem that we left with right now was that we could query large-scale data, but it was very complex to query the data. Like, you had to write cumbersome MapReduce job for executing a very simple query. But all we really wanted to do was use SQL. So Hive metastore was introduced to solve this exact problem. And Hive metastore and Hive style table lasted for a long time, and some will say too long. And while they created like warehouse-like user experience of I'm writing SQL and getting results, there were still quite a few challenges that remained unsolved in big data processing. And Detective Lottie is here with us. Oh, sorry, I didn't skip. So Detective Lottie is here with us to walk through the unsolved problems. The first problem was transactional consistency. So although Hive metastore and Hive style tables brought SQL to big data processing, it didn't provide full transactional support, making it very difficult to ensure consistency reliably in like big data systems. The next problem was that it was very difficult to manage schema changes without breaking existing workflows or having to rewrite huge amounts of data. Next problem was performance and scalability. although they were operational in large-scale environments, they didn't make it to provide good enough optimizations to give satisfying read and write performance on the systems. Next, it was almost impossible to reproduce a data set at a specific point in time, which is extremely important for debugging and compliance. Next one was that when something went wrong, it was extremely difficult to heal from it instantly. It was difficult to understand what caused an issue, and even when we got it, so there was simply no big red button we could press to bring the system back to a healthy state. And last challenge for now, there was no easy or standard way to implement the right audit publish pattern that makes a separation between data, like producing data and publishing the data, adding an auditing phase between those two processes and preventing from bad data reaching production. We've covered quite a few challenges, so here is a recap of the problems that we went over. And solving them was quite a challenging thing. And I'm taking you back to the evolution process that we started observing. We were with Hive Metastore and Hive style tables that, while they solved key challenges in big data processing by bringing SQL support to big data, the need to solve the remaining challenges became increasingly clear at this point. And then came open table formats, with names you're all familiar with, such as Delta Lake, Iceberg, or Apache Hudi. And those open table formats, they were to Hive-style tables what Parquets were to CSV. They really shifted how we treated big data systems and could manage them. And why those open table formats were game changers? They brought to life some powerful features that were designed to operate at that scale. So open table formats introduced ACID transactions, making it possible to ensure consistency and reliability of large-scale systems. If we wanted to look at last week's or last year's table, so with time traveling, this became easy. We could query historical versions of the data. Open table formats also enabled schema evolution on large-scale systems without having to rewrite huge amount of data or breaking existing workflow by introducing features like adding or renaming columns or schema enforcement. And finally, those open table formats were designed to perform at scale. And to do that, they use techniques like data pruning, caching, better partitioning, advanced query planning, even optimized file formats, everything to speed up analytical queries. So solving those problems that we went over was quite of an ambitious task. So let's break it down and see how open table formats do. Did open table formats solve transactional consistency? Yes, I think they solved it pretty well. And schema evolution challenges? Check. Performance and scalability? They were literally designed to do that. So they did solve it very well. But here is where things are getting a little bit more interesting, because I argue that open table formats don't fully solve the next three problems. And I want to explain why. So let's break it down and look at them one by one. So with open table formats time travel capability, we could query historical versions of a table, enabling reproducibility at the table level. With open table formats, we could restore a table to a healthy state. But again, it was only a table that I could look at and restore to previous state. And write audit publish, I could shallow clone a table, check things on my table. But again, you get it. Open table formats are great, but they work at the table level only. But table level is just not good enough. And why is that? Because in reality, we don't manage single tables. We work across environments. And when we're working with data lakes, thinking tables is just like thinking of one piece of larger puzzle. OK, so all right, it's time for a short exercise. I promise it's not yoga, guys. So come on, be with me. Please close your eyes. Come on, I'll wait. Go on. Now, now think of the data you usually work with. 1 second. Think of the data you usually work with. Maybe some of you are thinking, I see bronze, silver, gold. Or I see my critical data sales project. Or I see data sources as far as eyes can see. But here is what I bet none of you is thinking of. Specific tables. Like, no one is waking up in the middle of the night thinking, table XYZ, the love of my life, right? Now, let's take a moment to pause, thank our data, maybe whisper a quick namaste, and open our eyes. Because here's the deal. Tables are just the building blocks. When we try to reproduce data or recover from errors, we do that at the environment level. So now let's break it down and see what happens when we try to rely on table-level only solutions to solve the remaining problems. And a spoiler alert, it's not going to be very pretty. So let's talk about reproducibility and why it's such an important concept in our day-to-day work with data. So what reproducibility is, it's pretty simple. Reproducibility means that if I run the same process over the same input data, I get the same result every time I run it, as long as the process is deterministic, of course. So think about our data workflows. If I have a data workflow that like reads data, does some processing on it, and then writes the data output, and now if I want to change this workflow or tweak it a little bit to like get some improvement, so I have to make sure that I'm working from the same baseline, because otherwise, if my results change, I can't tell if it's due to my input data changing or due to the code modifications that I made. And reproducibility is especially important when the data we deliver impacts customers, which is almost always the case, right? Because when we work with data delivered to customers, if something goes wrong, we want to be able to first figure out what happened and then fix it ASAP. Now, let's take an example. And imagine that you're a data engineer working at Spotify in the team that is building the Discover Weekly playlist. And this playlist is generated based on some user listening habits or like local trends, etc. And let's try to build something reproducible. A disclaimer, all of my examples are using Delta Lake in the syntax, but all are applicable to any other table formats, just like the commands naming might change. So here, I'm looking at the liked songs table. And if I run this SQL query today, I get certain results. But what if I run it tomorrow or a few months later? Results may change. And why is that? Because the user may have liked some additional songs or something in the table was updated or changed. But here is where like Delta Lake time traveling comes in. Because Delta Lake time travel allows us to query specific historical versions of the data. And now I'm assured that if I run this exact same SQL query today or any other time, I get the exact same results. Remember, same code, same input, same result. But things get messy when we're dealing with more than a single table. Because this is really difficult to select the correct version of each one of those tables. It's an endless process. Like, it's doable, but you have to like use lots of bookkeeping and make sure that your input is aligned to the exact same point in time. And honestly, it gets really confusing. Now, let's talk about reproducibility. So people from your team starting to like sending you this kind of Reddits, and you understand that people are annoyed by the results of the latest like release that you published. So now, as a good data engineer, you're starting to debugging, troubleshooting, to understand what went wrong. If it was only the liked songs table that was corrupted, then we could use Delta Lake restore functionality to bring it back to a healthy state. But how would you go about rolling back hundreds of production tables? How would you even understand where to get started from? Last problem that open table formats don't fully solve is making it possible and easy to somehow implement the write audit publish pattern. And let's talk about the write audit publish pattern. And who heard of it? For those of you who haven't, it's pretty straightforward. I write data, then I run some automated checks on that data. And if the test passes, then I publish the data for consumption. It's like CI/CD for data. And why do we care? Because in reality, things are much more complex. Like usually, it's not only a single producer and single consumer. We have a much more complex dependency graph within our system. And there is one process that is writing to bronze, another process is aggregating to silver, and everything else is consumed downstream. And when something breaks earlier in the process, so like errors cascade. And the worst case scenario is that the data looks fine, but it isn't. And your data consumer is starting to propagate like data errors downstream. And the system, like as a whole, gets affected and looks something like that. And this is why like it's really important to be able to like implement this pattern into our day-to-day work with data, because we want to prevent such issues from cascading. Now let's try to use Delta Lake to implement something like write audit publish. So I'm looking at the recommendations table that stores personalized recommendations that are used by the Discover Weekly feature that we're working on. And if I want to work on changes to that table, I can use Delta Lake shallow clone functionality and create a shallow clone of the table. Now, I can work on the copy of my table in isolation. And by the way, shallow cloning, it means that I'm cloning the table without duplicating data. So it's pretty easy and very useful. So I'm working on that table, and I do my transformations. And once I'm done, like I'm running some SQL validations that make sure that my recommendations are accurate and they're what the user wants to see. But there are two challenges here. One is very similar to what we talked about with reproducibility and error recovery, is that we're now looking at a single table. Like, think of doing the same process for multiple tables, like hundreds of tables. Even if you do it for 10, it gets complicated, right? But there is another challenge here, which is like Delta Lake and other open table formats, they don't provide smooth way to publish changes after auditing them. So like if I ran those SQL validations and I'm confident that my change is good and I want to like publish the data, I need to make a decision now, right? Like, do I switch to the clone table? Do I rerun the transformation on the original table? So there are things to decide here. And what's really missing here is a smooth process that allows me to publish data without losing the ability to audit on multiple tables. So let's recap the problems that we argue that open table formats don't solve fully. So we understand that how those formats don't solve reproducibility, error recovery, and write audit publish. And I'm going to take you back to the evolution process that we were observing and tell you that the next level thing that came to life to solve those problems was data version control systems. And data version control systems were developed with the understanding that those problems that we're looking at are already solved in software engineering. In software engineering, if I want to reproduce something, then I inspect my Git commit log, and then I check out specific commit. And if I want to recover from an error, I just revert. And write audit publish, like CI/CD, it's an implementation of write audit publish. So just like Git for software engineering, data version control system bring engineering best practices to data. Now, I bet you remember Lottie, the axolotl. He's here also, and it's the lakeFS mascot that is not just here for looks. It represents lakeFS, which is the data version control system that solves those challenges. And lakeFS fits right at the heart of your data workflow, ensuring that everything from ingestion to analytics can be versioned, audited, and rolled back if needed. And let's see how lakeFS works in just 30 seconds. lakeFS is a data version control system that enables Git-like functionality on top of your object storage. It enables you to manage billions of objects or petabytes of data. lakeFS sits on top of your object storage, transforming it into what looks essentially like a giant Git repository, and enriching it with versioning capabilities that we believe are missing from an object storage. Things like commit, revert, merge, create branch, everything is available with lakeFS. Now, you can decide whether you want to version your data with lakeFS or you want to continue and directly write to your object storage as you did before. And the nice thing is that in order for your application to read and write data from lakeFS, you only have to reference lakeFS versions or branches. And that's about it. lakeFS is format agnostic too, which means that it works with any formats you have on your object storage systems, if it's Iceberg, Delta Lake, or unstructured data as well. And lakeFS works across them all, and you can use also any combination of your like. lakeFS provides an API, UI, CLI, SDK in multiple languages, you name it, everything to make the interaction with the system very smooth. So now let's see how we can use something like lakeFS to solve reproducibility, error recovery, and write, audit, publish. So with lakeFS, instead of wasting time tracking down what tables to look at in order to reproduce a specific state, you can simply refer to a lakeFS tag. And lakeFS tags have meaningful names, and they represent meaningful events in your workflow or like key checkpoints. And by pointing to those, by referring to those tags, you basically get those tags automatically point to the correct version of each table, which simplifies the process and makes it much more reliable. And this is how it looks like in the lakeFS UI. Tables are essentially collections of objects, as you see. Now, I'm moving to talking about error recovery. If we have a problem, all we have to do is find the commit that broke things down and then revert it. And this is how you do it with the lakeFS Python SDK. So essentially, we got a big red button we could press and heal immediately across tables. Like not just one table, I could revert a change at my data lake scale. And finally, let's see how write, audit, publish works with lakeFS. So if I want to implement the write, audit, publish pattern in lakeFS, so first thing that I'll do is create a lakeFS branch, which is, by the way, a metadata-only operation that does not duplicate any data. Then I'm going to define a lakeFS hook that adds some validations to my recommendations before merge happens fully. Then, when I'm done making changes that I write to my branch, I'm writing the output of my transformation to the isolated branch I created. And when I'm done making changes, I'm trying to merge. Now, the pre-merge hook that I defined will run. And if it will pass, the merge will be successful. Otherwise, it fails. Now, after we've seen that things look pretty good and we have solutions for all these problems, because data version control systems such as lakeFS work across tables and datasets, structured and unstructured, there is an exciting part here that I can tell you that we can do even more. And what we can do is to treat tables the way we want to treat them. And I argue that the way to interact with tables is through catalog, rather than through object storage path. And with the versioned catalog that is now coming, we're shifting from looking at datasets at the objects level to looking at them at the table level. And by using the right level of abstraction, we're shifting to working with our tables in a more intuitive way, but still getting the guarantees that data version control system give. So the version catalog enables Git-like functionality on top of your catalog, and it works across tables. And if you were asking yourself what products out there do version catalog, so lakeFS for Databricks is the answer for that. lakeFS for Databricks is a new release product that is a dataset versioning solution that was designed for Unity Catalog, and it allows versioning Delta Lake tables that are stored within Unity Catalog. How it works? You continue to work with your tables directly via the Unity Catalog, and you use the lakeFS for Databricks CLI tool to do versioning operations, such as create branch or commit, and which means that lakeFS stays outside the data path and observing the changes that you're making to your catalog. And why you use it, why you would want to use it, to continue to get the same guarantees you get by data version control systems, but continue to work with your tables the way you're used to. So you're in luck. We're here at booth 748, and we're showing lakeFS for Databricks. We will be happy for you to come visit us. Thank you very much for your time.